Welcome to College Algebra, Chapter 3, Section 5, where we're talking about rational functions and their graphs. This is a lengthy section. There are 9 pages of notes. I've been slacking on timestamping, but I'm telling you right now that as soon as I'm done recording this and uploading, I'm going to go in and timestamp. So if you want to be able to go from topic to topic or go back and revisit a certain topic, check out my notes on this video so that you can get right to where you want to go without having to watch what might end up being a lengthy video. All right, let's get into this thing. What are rational functions? Rational functions are functions that look like fractions. We've got a polynomial in the numerator and a polynomial in the denominator. Here's an example. Oh, first, very important, let's have a comment on the domain. The domain of a rational function is all of the x values except for the ones that would cause the denominator to equal 0. So, let's find the domain of this function. An x value of positive 2 would certainly cause this to equal 0. An x value of negative 6 would cause this to equal 0. So we don't want to include those x values in the domain. So our domain will be all of the numbers from negative infinity up to negative 6, or any of the numbers between negative 6 and positive 2, or, that's the union symbol, any of the values from 2 up to positive infinity. And that's it. That's your domain. No sweat. We're going to talk about what happens graphically when x equals 2 and negative 6 as part of this conversation. So the most basic rational function is called the reciprocal function. It is the function 1 over x, and the graph of it is here. And you'll notice a couple of things. One is the curve, whether you're approaching from the left or from the right, it appears that it never actually touches the y-axis, and that's true. As we come in on this graph from the right, our curve goes up and never actually touches the y-axis. As we come in from the left, our curve starts getting lower and lower, but it never actually ends up touching the y-axis. Why is that? Because, well, one reason is because an x value of 0 is not in the domain of this function 1 over x. We can't divide by 0, so our function actually isn't defined for x equals 0. So there's no point on this curve that has an x coordinate of 0. What's happening on the y-axis is what's called an asymptote. We're going to talk about that a little bit more as we go along. It also happens that, on this graph, as we move out toward an x value of positive infinity, our y values get lower and lower, closer and closer to the y-axis, or the x-axis. It looks like, as we go off to the right, like our curve is trying to land on the x-axis, but it's never going to. And as we head off to the left toward negative infinity, it looks like our curve is approaching the underside of the x-axis, and it is. However, that curve's never going to touch the x-axis either. So the x-axis is also an asymptote. It is going to be, or we call it a horizontal asymptote, as opposed to here, the y-axis is a vertical asymptote. What happens as the x values approach 0 in the first quadrant? We talked about that. The curve goes up toward positive infinity. Express this in arrow notation. So the things that we were just talking about while I was drawing with that purple highlighter can be written like this. As our x values approach 0 from the right, or from the positive side, our y values went curving up toward positive infinity. And the reason that I put that plus sign next to the 0 is to indicate that our x values are approaching 0 from a particular direction or from a particular side. Oh, I don't know why that just happened. That's a lot of me, though. There we go. Now I'm small again. And my cat is small, but she's just a real pain in the rear. Let's see if she'll just sit tight. So it means as x approaches 0 from the right, correct what happens as the x values approach 0 from the left or in the third quadrant. And the answer to that was our curve went down like this along the y-axis. So as x approaches 0 from the left or from the negative side, our y values approach negative infinity. So our curve dives down toward negative infinity. As x approaches 0 from the left or from the negative side, y approaches negative infinity. Express in arrow notation what is happening as the x values approach negative infinity. So as our x values go way off to the left toward negative infinity, our y values approach 0. They're only approaching 0. They don't ever actually become 0. We're just coming up on the underside of that x-axis, but never actually touching the x-axis. So here's a little synopsis of what those arrow notations mean with the little pluses and minuses on them. And now let's get a little bit more serious about our conversation about vertical asymptotes. So the function f of x equals 1 over x has a vertical asymptote. It's the y-axis. Our curve approaches the y-axis but never actually touches it. Excuse me. The y-axis has an equation associated with it, and that's x equals 0. Every point on the y-axis has an x-coordinate of 0, so we would say also that x equals 0 is the vertical asymptote for this function. It's not always going to be the y-axis. X equals a could be our vertical asymptote. Our function could be approaching it from the right and curve up along that vertical asymptote. Our function could approach from the left and curve up along that vertical asymptote. It could come in from the right and dive down toward negative infinity, or it could come in from the left and dive toward negative infinity. And having these examples, these illustrations with this language and this notation down here at the bottom, I think is really good if you wanted to copy these by hand into your notebook. If you have the ability to just do like a print screen or something, then I'll get off the screen if you wanted to take a screenshot of this and then print it later and be able to put it into your notebook. Not a bad idea for review purposes. That's too big. There we go. How are we supposed to locate vertical asymptotes just by looking at an equation? Let's read what's in this blue box. This is sometimes fun. So if our function f of x is equal to a polynomial over a polynomial, p over q, therefore it's a rational function, and if p and q don't have any common factors, in other words, we can't reduce at all, look down at example 2. You'll see down here, nothing can be canceled out there. That's what they're talking about. And a is a 0 of q of x, so some number a can be plugged into the function q, causing it to equal 0. Q of x is the denominator. Thanks for pointing that out for us. Then x equals a is a vertical asymptote. Okay. I feel like I want to understand that. Always nice to see it with an actual problem, where we can use some real numbers. What x values would cause our denominator, q of x, what x values would cause our denominator to equal 0? Well, I think that an x value of 0 or an x value of positive 3 would cause the denominator to equal 0. Therefore, since an a value of 0 or an a value of positive 3 cause the denominator to equal 0, then x equals 0 and x equals 3 will be the equations of vertical asymptotes for the graph of this function. Find the vertical asymptotes. X equals 0 and x equals 3. Those are your vertical asymptotes. So you'd have a graph and you would have a vertical asymptote here where x equals 0, in other words the y-axis, and at 1, 2, 3 you would have another vertical asymptote. And I don't know where the function is. Square. Maybe it looks something like this, and then maybe it looks like this, and maybe the right hand part of it looks like this. I don't know, it's just a guess, okay? But that's how the graph might interact with those two asymptotes. Don't quote me on this. If you want to draw a graph of what it looks like, use your graphing calculator, go to desmos.com, DESMOS, and type this thing in. Use lots of parentheses. Make sure the numerator goes in parentheses. The whole denominator has to be in its own set of parentheses, otherwise it won't graph correctly. Those were vertical asymptotes. What about horizontal asymptotes? We talked already about the graph of f of x equals 1 over x, and we said that the x-axis, the horizontal axis, was also an asymptote because our graph never quite touched that x-axis. The x-axis has an equation. It's y equals 0 because every point on the x-axis has a y-coordinate of 0. Therefore, its equation is y equals 0. Is the x-axis, if there's going to be a horizontal asymptote, is it always going to be the x-axis? No. You could have a horizontal asymptote that is above or below the x-axis. It'll have an equation, y equals some number, and our function can come up from underneath it and approach it. Our function could come in from the top, like an airplane kind of landing on a runway, except it never actually lands. Sounds like torture, doesn't it? And it's possible that your function can cross the asymptote when your x values are pretty small and you're like near the y-axis. But as your x values get really big, whether in the positive or negative direction, that's when a graph will tend toward an asymptote. We never concern ourselves when we're really, as far as horizontal asymptotes are concerned. Okay, as far as horizontal asymptotes are concerned, we don't really inspect a horizontal asymptote when we're near the y-axis. We're talking about x values that are big. 10, 50, 100, 1,000. As x goes toward positive infinity, what are the y values trending toward? Or as x goes to the left, toward negative infinity, what are the y values trending toward? That's typical language when we're talking about a horizontal asymptote. And you're seeing that language down here. There it is again. I like that this is printed for you so you can use that as reference. I will clear this, all these circles, just in case you want to print screen that. Let me get out of here for a second for you, just in case you can screenshot that. How am I supposed to determine or locate horizontal asymptotes? It's a little test, okay? It's one of 3 different possibilities. First of all, let's look at this very generic rational function that we have here. The numerator is a polynomial. The denominator is a polynomial. The numerator is a polynomial of degree n, The denominator is a polynomial of degree m. It's the largest exponent in the numerator and in the denominator. Can n and m be different numbers, different degrees? Yes. Can they be the same? Yes. Okay. This number a sub n is what's being called the leading coefficient in the numerator, and b sub m is the leading coefficient in the denominator. We may need those numbers. Now, if the degree of the numerator is less than the degree of the denominator, then the x-axis, or y equals 0, will be the horizontal asymptote for your graph. If n is greater, that the degree of your numerator is greater than the degree of the denominator, then you will not have a horizontal asymptote. And if it happens that the degree of the numerator and denominator are the same, then this will be the equation of your horizontal asymptote. Y equals leading coefficient over leading coefficient. If you can figure out a way to remember those three scenarios, great, great. I will share with you how I remember them. I think of three equations that I'm familiar with. Y equals x squared. Let's see. I'll do them in the order 1, 2, 3. Let's do y equals x over x squared, which is a little silly because this is really 1 over x. But the degree of the numerator is less than the degree of the denominator, and I know what the graph of this looks like. We saw it printed for us earlier. It's this one. And this one definitely has the x-axis as the horizontal asymptote. All right? So that's where the degree of the numerator is less than the degree of the denominator. So that's number 1. Number 2 is where they're the same. How about y equals x over x? Let's make it 2x over 3x even. Okay, again, it's ridiculous. But the degree of the numerator and the degree of the denominator are the same. Therefore, the horizontal asymptote will have the equation y equals 2/3. So our horizontal asymptote, our h-tote, will have the equation y equals 2/3. But of course, the entire graph is really 2/3. So it's a little bit stupid of a way to remember this one, but hey, do what works for you. I'm just telling you what works for me. Don't judge. I won't judge whatever silly mnemonic you come up with, or a song, or a poem, or a rap, or whatever it is that you call limerick. If it's a limerick, see if you can direct message me somehow. That'd be fun. Y equals, let's do x squared over x. Here, the degree of the numerator is larger than the degree of the denominator. This function simplifies to y equals x. I know what that graph looks like. It looks like this. Does that graph have a horizontal asymptote? Please say no. It sure doesn't. So that's how I remember that if the degree of the numerator is larger than the degree of the denominator, then I will not have a horizontal asymptote. Whew. Find the horizontal asymptote. Great. Examine the degree of the numerator and denominator. Numerator is degree 2. Denominator is also degree 2. Therefore, horizontal asymptote has equation y equals 15 over 3, which reduces to y equals 5. That's the equation of your horizontal asymptote. Piece of cake. If I change this exponent to a 1, then we don't have a horizontal asymptote anymore, because the degree of the numerator would be larger than the degree of the denominator. If I change this exponent to a 1, then the degree of the denominator is larger. And so the x-axis, or y equals 0, would be the horizontal asymptote. Yeah, so using transformations to graph rational functions. You have gone through a lesson already about horizontal shifts and stretches or shrinks or reflections over the x or y axis. These are a couple of common rational functions. 1 over x on the left and 1 over x squared is on the right. And it should be noted that these two graphs exhibit different kinds of symmetry. The graph on the left exhibits symmetry about the origin. At the very bottom left of your screen, it's being called origin symmetry. And what origin symmetry means is that if you pick a point like this one, and you draw a line from there to the origin, and then you travel in the same direction, the same distance, you'll end up at another point on your graph. That works no matter which point you select from the top right. If you sort of fold it over the origin, you'll end up at another point in the bottom left, or the third quadrant. You can determine if a function has that kind of symmetry by testing to see if it's an odd function. It's an odd function if f of negative x equals negative f of x. And there's probably been, we've seen a lesson on that also when we're discussing symmetry. On the right-hand graph, this graph exhibits symmetry about the y-axis. I like to think of it as butterfly symmetry, so you can, or a book, right? So it exhibits this kind of symmetry where you can take the right-hand part of the graph, fold it over the y-axis, and it will land exactly on the left-hand side of the graph. So that's y-axis symmetry, or symmetry about the y-axis. And functions that are even exhibit that kind of symmetry. And you can test to see if a function is an even function by determining if f of negative x is equal to f of x. Graphing rational functions. There's this very simple and straightforward 7-step technique for graphing rational functions. It's so much fun. We've talked about most of these in this section. So the first thing you can do is test for symmetry to determine if your graph is going to exhibit any kind of y-axis or origin symmetry. Then finding some specific points that you could plot. Number 2 tells us to find the y-intercept if there is one. Maybe you've got an asymptote on the y-axis, in which case there's no y-intercept, but maybe there is one. You can find it by plugging 0 in for x. We could find some other points. If you have any x-intercepts, you can find those by taking your function and setting it equal to 0. And then we go into the stuff that we've just been talking about, finding vertical asymptotes by looking for x values that cause the denominator to equal 0. Number 5, we could find horizontal asymptotes, if there are any, by comparing the degree of the numerator and denominator. And number 6 recommends that once we have found x-intercepts and vertical asymptotes, that we plot some additional point, at least one, in between the x-intercepts and the vertical asymptotes in order to get a feel for how the curve acts between the x-intercept and the vertical asymptote. I mean, if I had a vertical asymptote here and an x-intercept here, great, so my curve passes through that x-intercept. which way does it go? Don't know. I should probably plot a point that has an x coordinate that's here so that I can just find out, is my curve going to pass through this point up here, or is my curve going to pass through this point down here? That will help me see which way my curve should be going. This way or this way. Boop, too far. Ready to do some graphing? First, let's test for symmetry. Let's test for negative x isn't going to work. If we negate the whole thing, let's try that one. Let's see if this function is odd. So number one, odd question mark. In other words, is f of negative x equal to negative f of x question mark? Let's find out. What is f of negative x? F of negative x is 4 times negative x over negative x squared minus 1, which equals negative 4x over x squared minus 1. And what is negative f of x? Well, if we just negate the entire function, look up here, look at the original function up here. Let's just multiply that thing by negative 1. If we multiply that rational function by negative 1, we can multiply a negative 1 into the denominator. We could put a negative sign to the left of the fraction bar, or we could multiply the numerator by negative 1. Let's multiply the numerator by negative 1. Hey, would you look at that? negative f of x equals f of negative x. Therefore, our function is odd. Odd functions, remember, exhibit symmetry about the origin. All right. The second thing we want to look for are y-intercepts. How do we find a y-intercept? We plug in an x value of 0. Can we plug an x value of 0 into our original function? Will it accidentally cause division by 0? 0 squared minus 1 equals negative 1. So no, we're okay. So to find the y-intercept, find f of 0. F of 0 equals 4 times 0 over 0 squared minus 1, which is equal to 0, because we have a numerator of 0, a denominator of negative 1, and so 0 divided by negative 1 equals 0, which means we can plot our y-intercept 0, 0. I'm going to plot that point right away. The third recommendation is to find x-intercepts. To find an x-intercept, we will solve f of x equals 0. In other words, we're letting y equal 0 and then solving for x. Setting my original function equal to 0, I see that the only way to make a fraction on the left-hand side of this statement equal to 0 is for the numerator to be 0. So we need 4x to equal 0. And there's only one way to make that happen, and that's with an x value of 0. So we can plot, this is an x value of 0, we started with a y value of 0, it's the same point. So it turns out that our x-intercept and our y-intercept are the same point. Our graph's going to pass through the origin. The next thing we're supposed to do is find vertical asymptotes. Vertical asymptotes are determined by checking to see what x values will cause our denominator to equal 0. These notes have been referring to the denominator as the Q function, which is equal to, in this specific example, x squared minus 1, and we're going to set that equal to 0. We'll add 1 to both sides. Take the square root of both sides, and what's the square root of 1? Careful. There are two answers. The answer is plus or minus 1. So we have two vertical asymptotes. One is at positive 1 and the other is at negative 1. I'm going to graph those right away before I forget. We could put arrows on the tops of them and the bottoms if we like. And then number 5 in our to-do list says that we should look for horizontal asymptotes. Remember that we determine horizontal asymptotes by comparing the degree of the numerator and denominator. In this case, the degree of the numerator is less than the degree of the denominator, which is a lot like 1 over x. And since the degree of the numerator is less than the degree of the denominator, we know that y equals 0. In other words, the x-axis is the horizontal asymptote. So let's go to our graph and put a dashed line along our x-axis. There we go. And next, we're supposed to plot some points that are between our x-intercept and our asymptotes. Which means we want to choose an x value perhaps of positive 1/2 and negative 1/2. And then we should probably also choose an x value that is on the outside of our asymptotes. So maybe we use an x value of 2 or 3, and maybe negative 2 or negative 3, just to get a feel for which quadrant is our curve going to be in. So we've got 4x over x squared minus 1. And let's test f of 1/2. So I'm going to use a graphing calculator here. And I'm going to go to my home screen. And I'm going to type in 4. And then I'm going to hit this X button over here, which has a few different variables on it. It's got an X and a T and a theta and a lowercase n. So this is just right on the home screen. I'm typing this 4x divided by, open parentheses, x squared. The square button is in this left-hand column. X squared minus 1, close parentheses, enter, and I get some weird number that I wasn't expecting. Now I want to take the x value of 1/2 and I want to plug it into this expression that I just typed onto my home screen. So I'm going to take 1/2, or you could type 0.5. So I've typed 1/2, and then I'm going to hit this button down here, which says STO with an arrow. That's the store button. It puts a little arrow next to the 1/2, and then I'm going to hit my variable x again and hit enter. And on the right-hand side, all I did was type 0.5 for me. So now, in order to get that 0.5 to process through the original expression that I typed in that's still at the top of my screen, I'm going to hit second. There's a little second button up here. And I'm going to hit enter in the bottom right corner. This is a TI-84, by the way. So an 85 or an 87 maybe functions differently. I think you can just scroll up through your previous entries. Now I'm going to hit second enter again, and it has recalled the expression that I entered, 4x divided by x squared minus 1. Now when I hit enter, it processes our x value of 1/2 through that expression, and I got negative 2.6 repeating. So we're going to have to plot the point 1/2 comma negative 2 2/3. Now I'm going to type in a different x value. I'm going to use negative 1/2, so negative 1 divided by 2, store. I'm going to store it in the x value, or the x variable. Hit enter. On the right hand side I see negative 0.5, and then I'm going to hit second enter, so that I see my expression of 4x divided by x squared minus 1. I hit enter. It processes that x value through the expression, and I get f of negative 1/2 equals positive 2.6 repeating. And then let's use an x value that is to the right of our rightmost asymptote. Let's try an x value of, what was it, 3, 9, 8, 4, 3 is a little rough. 2 isn't any better. 4 makes that a 15. That's not good. 5, 25, 24, 20. Nothing's really great. Let's use 3. So I type 3, store, x, enter, second enter, enter. And I get 1.5. So f of 3 equals 1.5. Before I put a negative 3 in, let's go up and graph these points. So I've got 1/2 comma negative 2 2/3. That is negative 1/2. Wait, what was it? Positive 1/2, negative 2 2/3. Down 1, down 2, down 2 2/3. So maybe here. And then another point that we plotted, or that we calculated, was negative 1/2. We plugged in, and we got out a y value of positive 2 2/3. Negative 1/2 up 2 2/3 puts me about here. Am I surprised? No, I'm not. Why am I not surprised? Because we figured out that this function was going to be symmetric about the origin. Therefore, I knew already, even though I did the calculations, that this point could be reflected across the origin, right? We come up to the origin, and then we go the same distance in the same direction. So we came up to the origin, and then we kept going, and we arrived at another point that's going to be on our graph, because we're working with an odd function, which has origin symmetry. Okay, let's take that idea, and also we have 3 comma 1.5. Let's plot that point to the right. 1, 2, 3, up 1.5. Puts us here. That was supposed to be blue. over 3 up 1.5. Here we are. And we should be able to take that point and just fold it over the origin and end up at another point. Let's see if we get even close. Right. It'd be helpful. It's helpful that I'm using a ruler, actually. So my distance looks like about 3.5 units. And so if we go take it out to 7, I should end up like maybe here. -3, -1.5. That is definitely correct. If you'd like, we can pop back down here and write in that f of -3 is equal to -1.5. And can we draw our curve finally? Are we done with all of our stupid steps? Yeah, I think we've abided by all of the requirements. And number 7, we're instructed to actually sketch a curve. I would say that when we're in here in the middle of our graph, between our vertical asymptotes, I'm going to draw my curve to stay pretty tight to that leftmost asymptote. It's going to pass through this point. It's going to keep coming in and hit the origin. And then as it goes through, it'll catch this point and then keep easing its way out toward that vertical asymptote. Go down forever. On the top left, at the end of that curve, it's going to go up forever, staying sandwiched in between those asymptotes. And in the first quadrant, since we know our curve has to pass through this point, and we've got that vertical asymptote of x equals 1, I'm very confident that my curve is going to come down here like this and pass through this point. What I don't know is my curve going to stay in the first quadrant, or could we see this anomalous thing where the graph crosses down and then maybe comes up and then starts to follow that asymptote? It's possible. Either that's going to happen, or our curve will just stay up here. How am I supposed to figure that out? Well, you could plug in an x value of 5 or 7 or 8 or something and see, do you end up with a negative y value? That would tell you that you're going to cross over. Or punch it into a grapher, see what it looks like. In the third quadrant, if we follow what we did in the first quadrant, and we should because our graph has origin symmetry, this graph should come up through here, pass through that point, and curve out this way. Nice job graphing your rational function. Let's see, is there any quick way for me to... Let me pause and see if I can show you what the actual graph looks like. And here we are in Desmos. This is desmos.com, and I punched in... Oh, it's behind my head. Can I move me? I can hide me. There you go. There's our equation in red, and there is the graph, and it looks to me like our graph is staying above the x-axis all the while. And you can just drag your way out there. It just keeps getting closer and closer, and you could zoom in and see just how close it's getting. And then, now I'm not on a, so I'm not doing this on a computer, this is on a tablet, but I am able to use my pen and just touch the curve, and it's showing me coordinates 53, 0.0751. So just slightly above the x-axis. And hitting the home button in the top right corner there took me back to my original graph. Nice, so this is looks pretty accurate. I wonder if we could, let's see if we can do this too. I'm gonna hit the plus sign, no. Can I just, oh, I just tapped below there, and now I can type in x equals 1. There's a vertical asymptote. I wonder what this step does. No, don't do that. How do I undo that? There we go. And then we could click below that, and we could have x equals -1. So there are two asymptotes. Looks pretty good. Right then, back to work. Amazing. Look at that. It just snaps right back to our extremely accurate hand-drawn graph. That was fun. Gotta get your kicks everywhere you can. No way, there's another kind of asymptote. There's a slant asymptote. Unbelievable. I didn't even know there was such a thing. Did you? There's slant. I'm just kidding. I knew they were there, but really, slant asymptotes. Okay, how do we deal with these things? So the graph of a rational function could have a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. That's got to go into your notes somehow. Slant asymptote only happens if the degree of the numerator is 1 more than the degree of the denominator. Okay. P and Q and no common factors, and the degree is 1 greater. Great, find the slant asymptote by dividing Q into P. In other words, we have to do the division. And when we do that division, we're going to get an answer that looks like this. And we know it's going to look like this because the degree of the numerator is only 1 larger than the degree of the denominator. So if you had like x to the 5th divided by x to the 4th, you're going to get x to the 1st power. So it shouldn't be a big surprise that this is what the result of the division is going to look like. And then even after I do that division, what's the equation of the slant asymptote? Just this part. Disregard the remainder. Your slant asymptote's just going to be the mx plus b part. So let's do some long division, and then I'm amazed. We're at the 47-minute mark right now. I'm impressed that it only has taken this long, because this has been a lot of content. We're going to take x squared plus 0x minus 9, and we're going to divide by x. X times what equals x squared? The answer is x. And then we do x times x, and we get x squared. We do the subtraction, get 0, bring down the 0. X times what equals 0? This is a weird problem. The answer is 0. So plus 0. And then 0 times x makes 0, and 0 minus 0 is 0. Bring down the -9. X times what equals, oh, and -9 is the remainder. Haha. So that's our, I'm starting to lose it. Okay. -9 is our remainder, plus -9 over x. Don't really care what the remainder is, because the mx plus b is right here. This is what we're using for our slant asymptote, so it looks to me like our slant asymptote is y equals x. Jump back over to Desmos, graph this as your first equation, graph the original function as your first equation, and then graph this as your slant asymptote, and see if it works. See how quickly maybe the curve gets over to that slant asymptote. Applications, are there applications to these types of problems? Without a doubt, the crazy numbers of applications. Finding out where those zeros happen, and where you've got sign changes, and there are business applications, financial, economic applications, without a doubt, physics applications. The list goes on and on. But we're not going to make that list because we're just shy of 50 minutes and I'm ready for a break. Plus, I've got time stamping to go do. I'm going to get to it. You've got work to do too. See you next time. Thanks so much.